Hello wonderful person, this is Anton, and in this video we're going to be talking about a very interesting discovery of galaxies that were right in front of our face, but we just didn't see them. And I'll also try to briefly explain to you why the night skies are dark. So a few months ago I made a video about the image from Hubble that sort of blew my mind. It was an extremely large image of hundreds of thousands of galaxies all in one. I've also kind of talked about why we don't really see everything on this image, but I guess the biggest point I wanted to make and want to make right now is that all this dark space that you see in between galaxies, although it does seem dark, it's not really dark. There's actually stuff there, or there used to be stuff there. And so for example here, if I were to start zooming in to various dark spots in here, I would actually start seeing things. And for the most part, at some point I would start seeing galaxies that are really far away, or maybe even the early light from the universe. But also some galaxies we're not able to see anymore because they're beyond the so-called observable horizon. We can also quite easily simulate this in Space Engine by looking at the night skies and then by increasing the actual magnitude of our perception, and you'll see that with time it will increase to the point where you start seeing more and more galaxies, more and more light. And as a matter of fact, what was invisible will now become visible. None of this was here before, but now, because we've illuminated the night skies, we can kind of see it a little bit better. At the same time, even the Hubble telescope is not able to see certain things because it doesn't really produce images in, for example, infrared light. And so here, there might be something in the middle, but we just don't really see it. And this is exactly what the scientists behind this paper in Nature magazine did. They took a look at the part of the night skies that obviously Hubble looked at before, and were able to discover optically invisible, really massive galaxies that were part of the early universe approximately 2 billion years after the universe was created. In other words, they were able to look back in time and see galaxies really far away, and also really massive galaxies that were made about 11 to maybe 12 billion years ago, and some of these galaxies were extremely massive. As a matter of fact, so massive that it really surprised the scientists behind this paper. But even though we can see these galaxies right here in Space Engine, none of these galaxies represent what we saw, because this is still visible light. They were able to detect the infrared light and also the microwave light that was otherwise invisible to us until now. So how did they actually do it? Well, they actually used multiple observations from various telescopes and used the really famous ALMA observatory that you can see right here. But at the same time, several other observatories, including the European Space Observatory's VLT, also known as Very Large Telescope. And so by using various frequencies and different parameters, they were able to pierce through all of this darkness and detect microwave and also infrared light. And that, of course, suggested that there were really massive, very unusual galaxies in those regions, 39 of them specifically. Now, prior to this, the only ancient galaxies we were able to observe from so far back in time were the so-called starburst galaxies. These are usually really small in comparison, and they're called starbursts because they're really bright. They also produce a lot of ultraviolet light, they're very energetic, and we also think that they usually consume about 1,000 masses of the sun per year in order to produce as much light as we observe. But all of these starburst galaxies are actually really small in size, and we believe that most of them probably just combined with other galaxies. So they weren't really representative of what we see in the universe today, because if you look around, today you'll see a lot of massive galaxies as well, and we don't really know how they were formed. So by detecting these previously invisible 39 massive galaxies, the scientists behind this paper actually showed us that, well, they were out there, they definitely existed, and they most likely evolved to be the really massive galaxies that we have today, including, of course, the super famous M87 galaxy that we were able to zoom in on and then take a beautiful photo that became really famous a few months ago. And so the origin of these galaxies, where these massive black holes reside, can now be kind of put to rest, because we now realized that these galaxies were always out there, we just didn't really see them because they were producing different types of light. And one of the main reasons these galaxies are practically invisible is because of the distances involved here. At this point, the light from these galaxies has been so redshifted that it turned into infrared and also microwave radiation. And also because a lot of these galaxies contain tremendous amounts of dust, much of the more energetic light is actually hidden from us. So the only light we can detect from them is not really the visible light, but more along the lines of low infrared to microwave light. And this is kind of what ALMA was able to do along with the VLT observatories. And if you were to compare wavelength of this light that we're able to receive from these dark galaxies compared to a typical light wave, it's about 1,000 times longer, or basically less energetic. The wavelength that they were able to receive are about 1 millimeter, which is actually basically microwaves or very low infrared light. It's almost impossible to detect it with any other telescope except for a very powerful radio telescope or new telescopes like the James Webb that's coming out in the next few years. Because by looking at these galaxies with the James Webb telescope that's coming out in the next few years, we'll also be able to identify various elemental compositions of these galaxies and study their chemistry, and then possibly the chemistry of the early universe. But there were a lot of other really interesting things that were discovered by the scientists behind this paper. One of them was that, well, first of all, these early galaxies were also quite active in the production of stars as well. They were producing roughly around 200 masses of the sun per year, which is about 200 times more stars produced than any galaxy near us today. Our Milky Way produces about 1.3 masses of sun per year. These galaxies are dramatically faster, about 200 times so. At the same time, the actual star production and the luminosity of these stars in these early galaxies would present us with a very different type of a night sky. Let me try to demonstrate this by using Space Engine. And so here we are on the surface of a random exoplanet somewhere out there in the universe, and the night skies in these types of galaxies would look something like this. They would be extremely populated, there would be stars everywhere. But all of these stars that you see are mostly nearby stars. We would not see any far stars or even far galaxies because of the amount of dust in this galaxy. Everything here would be basically kind of like local stars and local objects. And so a typical alien race with a telescope that may have existed back then somewhere out there in the universe, if they were to look into the night skies, they would not see galaxies, they would not really see anything too far away because it would be all hidden by dust. But they would still see this incredible view that you see in front of you. Lots of stars, lots of beautiful locations, all of it relatively close as well. They might even be able to go there, unlike us. We're kind of stuck here, we're pretty far away from even the nearest exoplanet to us. Hello wonderful person, this is Anton, and in this video we're going to be talking about a study that was able to investigate the technically most invisible part of our universe, the area known as Zona Galactica Incognita. So here on Earth, when you think about the most invisible part of the universe, you're not probably going to be thinking about what I'm about to show you. I guess in some sense it's very difficult for us to see what's right behind the sun. As a matter of fact, if this is Earth right here, the area right behind of the sun is technically invisible to us, which is why it served as a kind of a story plot for many different science fiction books. Now, that's not really what we're talking about, because we have seen that side using various telescopes that were sent over the years. However, there are parts of the universe that are, well, practically invisible to us. And although technically the farthest reaches of the universe do qualify as those invisible areas, we're talking about something a lot closer to home. So here, the area that I'm about to show you, that's essentially right there in the center of the Milky Way, behind the central bulge, is kind of invisible to us. The amount of dust and the amount of actual material facing us here prevents us from seeing what's behind. We don't really have a good picture of what might be behind all of this dust, behind all of these stars, and obviously behind the central black hole. And so we've named this area Zona Galactica Incognita, in other words, a known galaxy zone. And it's a pretty solid name, because if you were to look at the galaxy from the top, with Earth being selected right there on the bottom, right behind the bulge right there, this whole chunk of the galaxy is technically just simulated. We don't really know what stars are there, we have no idea if there are any major black holes or major pulsars or really anything. The vast amounts of dust and all of this gas that you see right here, all of this is so good at preventing us from discovering what's beyond that we didn't really hope to find it for quite a while. But it just so happens that certain parts of light spectrum can get through this dust cloud, and specifically certain parts of infrared light. And so by collecting various infrared light that's coming from those regions of the galaxy, we've eventually collected enough data to be able to analyze it and to be able to kind of see through and potentially discover certain stars. And it just so happens that today we've advanced so much in the area of artificial intelligence and machine learning that several algorithms exist that allow us to quickly discover stars in gigabytes and terabytes of various data that we can throw at it. And so that's kind of what the scientists behind this paper that was recently published decided to do. They took an algorithm that's usually known as CNN or convolutional neural network, and they threw all of this data at it, trained it, and let it learn to recognize what certain types of stars looked like. And then by collecting all of the data from the hidden region of our galaxy, they were able to discover over 1,000 different stars we didn't really know existed. And the types of stars they've selected are the so-called Cepheid variables, about which I've talked about previously. These are stars that are really well known to us. We are kind of dependent on them because these are pulsating stars. That's what they do, literally. They increase in size and increase in luminosity, and then decrease in size, decrease in luminosity. In other words, they kind of like breathe in a sense. And by doing this breathing, and also because they're doing this with a very specific pattern, we can usually use them to determine distances in space. So this is kind of how we discover distances to nearby galaxies, for example. Here's one example from the Andromeda galaxy, and you can see that as it changes color, and as it does so periodically, we can usually determine its maximum luminosity. And by using that, we can then determine the distance to the star very, very precisely. And that's because there is a very direct relationship between how bright they get and also how often they change their luminosity. So by using these relationships, we can usually very precisely determine distances, and by finding thousands of these objects, or just over 1,000 technically, the scientists behind this paper, for the first time ever, were able to very precisely point at where these stars were located and thus show us, in some sense, what the shape of the galaxy on the other side, on the dark side, was. Now, the dark side, or I guess the far side of our galaxy, hides a lot of mysteries, and specifically related to the number of potential arms, galactic arms, but also we don't really know if there are any warps there or not. Like, for example, if we were to look at a typical spiral galaxy, this is a simulation of the Milky Way galaxy, we know that they have spiral arms, and we know that some of them are symmetric, but some of them are not. Some galaxies have disturbed or broken arms, and some of them might even have tons of arms that we didn't account for. Or maybe there are only arms on one side, whereas the other side was either disrupted or has some kind of a break, or even a sign of a collision. And so all of this is really interesting to us because it will allow us to understand how our galaxy evolved over time, what collisions with other galaxies it may have experienced, and by studying the dark side we can also pinpoint the variations in dark matter, the interactions with dark matter. We might even discover more unusual mysteries, strange supernovas, strange black holes, or strange pulsars that we've never seen before. Now obviously we don't really know what's there yet, but this is a good start. By being able to combine the infrared light that does get through the unusually thick dust clouds that we have here, and then taking the artificial intelligence or the machine learning algorithms that are already really well established and quite well understood, we can definitely discover a lot more things out there that we didn't really know existed. Now, apart from discovering the locations of these stars, that is a pretty good discovery already, the scientists behind this paper were also able to discover the ages of these different stars. They realized that the Cepheid variables on the dark side, or on the far side technically, were actually youngest closer to the center. So younger stars were closer, older stars were a lot farther. And this is reflective of what we have on our side. So technically, in that sense, the distribution of Cepheid variables is more or less the same. Now, we don't really know if there is any difference, but in a sense, maybe that's not really an exciting discovery, but it is a confirmation that maybe that's how it is. Maybe the Cepheid variables that are younger are formed near the center and they spread across the galaxy and slowly move away and then eventually end up on the outskirts. We don't know why or how this happens. We just seem to be observing this on both sides of the galaxy. But the data from the study and also follow-up studies will definitely help us discover what really is the shape of our galaxy. Right now, this is all a simulation. We don't really know what it looks like. We have no idea how many arms we have or how many arms our galaxy has. We don't know if these arms are more or less rigid or if they're sort of broken up into pieces. And we also don't really know if our galaxy is warped everywhere, as I've mentioned in one of the previous videos, because this is something we've discovered not so long ago, or if it's only warped on one side and the other side is more or less flat and doesn't really have any signs of collisions or any other features. Now, it's possible that in the next few months, other follow-up studies will also be able to discover other unusual objects by using a very similar technique but applying it to other types of stars. But even though this study mostly focused on the infrared light or the near-infrared light to detect the Cepheid variables, we could technically use other wavelengths of light as well, specifically the longer wavelengths. We could use radio waves, for example. And so it's very possible that in the next few years, we might be able to map this whole region very precisely by simply using these longer wavelengths of light, and then by using machine learning to try to identify these objects that were not visible to us, simple humans. And although it's unlikely we're going to discover something super unusual or super weird, or something that we didn't really expect to find, it's still interesting to map this area because, I mean, it's our own galaxy and we might need to know more about our own backyard before we try to go and explore other worlds out there. Hello wonderful person, this is Anton, and in this video we're going to be talking about an unusual discovery related to galaxies, and specifically related to the evolution of galaxies, something that we really didn't expect, because some of those galaxies changed very suddenly. So when it comes to our own galaxy and also of course our own solar system, we're exceptionally lucky. The Milky Way galaxy that you see right here, and of course our own solar system inside of the Milky Way, are both extremely quiet. They're not particularly active, nothing major is happening in either one of them, and because of this, we believe life was able to evolve around our planet, while at the same time was able to sustain itself for billions of years. Had our galaxy been more active, it's very likely nothing would actually exist on this planet. Now, I've talked about quasars in previous videos many times, but the idea here is that there are galaxies out there that are exceptionally active. As a matter of fact, in one of the recent collaboration video I did with Fraser Cain, one of the questions was, could life exist around a quasar, around a galaxy that's extremely active? And to give you a short version of the answer, no, absolutely not. The amount of energy quasars generate creates so many gamma rays in the entire galaxy that it would literally destroy any life on any planet around the galaxy, even if it was relatively far away from the galaxy as well. So a quasar, which is a very powerful galactic emission from the middle of the galaxy, from the supermassive black hole in the center, basically destroys life. Now, luckily for us, our galaxy is not a quasar, but for the longest time, we believed that we understood how galactic evolution happens. Just to give you a short version of it, first small galaxies merge, they turn into the so-called starburst galaxies that produce a lot of different stars, then something triggers the quasar stage, and today we believe there are actually two different quasar stages, more powerful red quasar and the much weaker blue quasar, and then all of this evolves into a galaxy possibly similar to the Milky Way or any other galaxy near us. We've actually seen various steps of this process pretty much everywhere in the universe, and we've identified several different types of quasars, several different types of starburst galaxies, and this allowed us to understand how galaxies evolve and how they switch on, switch off, and create various types of emissions from the middle, from the supermassive black hole. But we've always believed that this transition stage from, let's just say, a starburst to a quasar, or from a quasar to a quiet galaxy, takes a long time, possibly thousands and maybe even millions of years. This is something that we kind of took for granted, mostly because we've never really seen galaxies change on the spot. Until now. So the paper that you can find in the description below was looking at these 6 galaxies you see right here. Their names are not particularly important right now, but the main point here is that they were not very active. They were what's called as liner galaxies, or low ionization nuclear emission line region galaxies. In other words, these are galaxies very similar to the very famous M104 or the Sombrero galaxy that you see on the screen right here, that have some emissions in the center, but they're not particularly powerful, and these are very specific emissions that we believe are caused by possibly occasional matter being absorbed by the black hole. In some sense, somewhat similar to what you see on the screen here. As the matter falls in, the emissions are released and produce this energy. As a matter of fact, some of the recent observations from Sagittarius A star, the supermassive black hole in the middle of our own galaxy, do suggest that something is causing our own black hole to kind of light up a little bit too, so it might turn into this so-called liner as well. In other words, it might produce a little bit more emissions in the future. But as they were looking at these 6 galaxies, they realized something was changing in them. For all 6 of these galaxies, their emissions were increasing dramatically. They were basically becoming a lot more bright and a lot more active, and doing so very, very quickly. And their first assumption was that, well, maybe what they're looking at is basically a typical supermassive black hole just having a little snack. Essentially, there is probably some sort of a star there that's falling apart, and as it falls apart, some of its mass is falling into the black hole, and thus the luminosity is increasing. But all of this was not so. As a matter of fact, within about 2 months' time, the luminosity of the black hole for all 6 of these galaxies has increased so much that all 6 of them technically turned into quasars. In other words, they were no longer liner galaxies, they were basically these really massive, really powerful quasar galaxies that were now emitting a lot of energy. In other words, they sort of skipped the whole starburst stage and then switched into the quasar stage and became very, very active and very energetic. And this is something that the scientists behind this paper couldn't really explain. Now, they believe that maybe this is actually just a new type of a galaxy we've discovered that switches from the liner galaxy type into the quasar for some reason or another. Or maybe we've witnessed something we didn't really expect to witness, some kind of a transitional stage that only happens in certain galaxies. In other words, we're not entirely sure what's really happening here. But there are some slight differences between a typical, well-known quasar versus what we're seeing here. For example, the bright region right now is only right at the center of the galaxy. But in most quasars, usually this brightness comes from the central region much wider than just the center itself. Now, it's possible that all of this will change over time, and maybe these 6 galaxies will actually become full-fledged quasars given enough time to evolve. But for now, they're definitely very different from other quasars we've observed. Nevertheless, though, all of these transitions were so sudden and so dramatic that we just don't really have any modern theories to explain what's happening here. For all we know, maybe this is actually something that happens in a lot more galaxies out there. And here's the scary part. What if this is something that can actually happen in the Milky Way galaxy? What if this is something that could potentially suddenly start around Sagittarius A star, and if this is something that can start so suddenly within only a few months without really giving us any notice, that could be a problem, because if our galaxy suddenly turns into a quasar, which I don't think it will, but if it does, we might be potentially facing an actual mass extinction. Because like I said before, quasars produce so many gamma rays that it will irradiate our planet to the point where nothing will survive. But that's not to say that it's going to happen. I'm just saying that we need to study this in a lot more detail to discover what's really happening in these galaxies, what caused this, and then we need to make sure to understand if it can actually happen in the Milky Way. And if it does happen in the Milky Way and we don't have a technology to escape the galaxy, well, that's game over. We're done. We don't really have any means of escaping the galaxy, and we don't even have any means of escaping our own solar system right now. Although, technically speaking, one science fiction-y solution to all of this would be to have our planet tidally locked to the location of Sagittarius A star. In other words, if this is the black hole and it's emitting toward our planet, then by having the planet always facing away from this region, the gamma rays only strike this side. The dark side, as you would call it here, would be pretty much protected from these gamma rays, and so in that sense would be maybe safe. But the problem, of course, is that gamma rays will also very likely strip our atmosphere and will probably slowly thin out atmosphere around the whole planet. So in other words, no matter what we try to do and no matter how we try to protect ourselves, once a galaxy turns into a quasar, or I guess the supermassive black hole in the middle does, that's it. That's game over. All life ceases to exist and basically the planet disappears. Actually no, the planet will still be there, it just won't be habitable at all. But I think the more interesting part here is really trying to figure out what happened in those galaxies. What could have caused such a dramatic transition of having a galaxy go from being somewhat active and possibly emitting some energy to suddenly becoming this extremely bright source, very powerful, and essentially reaching the next evolutionary step in its existence. And although today we don't really believe our galaxy, the Milky Way, is going to turn into one of these quasars for a very long time, it probably will become one once our galaxy collides with either the Andromeda galaxy or the Triangulum galaxy in about 2.5 billion years from now. So there is a chance that one day life on Earth will actually cease to exist after all. But will it happen anytime sooner? So this is something that we do want to discover, and this is something we want to study in detail in order for us to understand, I guess in some sense, when is it that all life on Earth finally ends. Now hopefully by then we'll be some kind of an intergalactic species able to cross very large distances in almost no time, but until then we do need to study this so that we understand it a little bit better. And actually, if you'd like to learn more about recent quasar discoveries, check out some of the videos that are popping up somewhere above my head right now, because there's actually a lot of stuff we've discovered about galaxies in the last few years or so, and some of this stuff is pretty exciting. Hello wonderful person, this is Anton, and as I was finishing a video on intergalactic medium, where I was going to explain to you what's happening here in between galaxies, yet another interesting paper came out with a new discovery and a new picture of something that we've kind of theoretically knew existed, but never really saw in actual real life. We're going to talk about the so-called cosmic filaments and the cosmic web, and the picture that you can see right here that represents what we were able to observe in this particular study. Now, to try to explain to you why this is actually very significant and why it's a very interesting, very important picture that despite its low quality is actually a very great achievement, I need to begin right here. What you're looking at is known as the Illustrious project. The link for this is in the description below, and it's actually one of the most complex ever simulations that is able to recreate universe as we believe it should be theoretically. In other words, it's a recreation of a real universe, but in computer terms. And if you follow me on Twitter, you may have seen that I posted the image you see on the screen right here. This is actually the representation of various universe simulations using various models. And Illustrious right here is actually free to use, and it's absolutely amazing in what it can create. So what you're looking at here is kind of like the visual spectrum of various galaxies and technically a galactic cluster that Illustrious was able to create. And here, if we look at the amount of gas that it can also generate by looking at the so-called gas density, we'll see that once in a while here, specifically if you look at the cluster from a distance, there are going to be these unusual filaments, these unusual formations that sort of connect everything together, these gas filaments that are spreading across the universe and that are technically connecting everything together, literally forming what's known as a cosmic web. Here's sort of what all of this looks like from a distance, and this is millions of light years across, with the actual galaxies being these tiny spots in the middle. And this cosmic web was always predicted, as you can see it's basically simulated in Illustris as a theoretical prediction, but unfortunately we've never really got a chance to look at it. Simply because the gas in here is so diffuse and so sort of low in density that it's almost impossible to take a picture of it, because the galaxies themselves overshadow the gas and make it almost impossible to see. In other words, we kind of always think of intergalactic space as this dark medium, but in reality there's a lot of gas here. Just as we've always believed and always calculated, most of the mass in the universe is actually here between galaxies. Most of the gas is literally stuck here and will probably never really form into anything. Now, we'll talk more about this in the intergalactic medium video, but for now what you need to understand is what we've actually discovered. So when the scientists behind the paper that you can find in the description below, this paper right here specifically, were looking around various galactic clusters, they discovered one cluster that's currently really ancient. It was actually approximately 12 billion years old when we were looking at it, so basically this was 12 billion light years away from us. And in this particular cluster, because it was so bright, the galaxies were actually much brighter than usual, they were kind of able to see certain things. Specifically, they were able to see, I guess you can call them sort of like reflections of various extremely bright galactic objects, such as, for example, the black holes in the middle of those galaxies, reflecting off the dust in between galaxies. So, in other words, imagine a really bright galactic center like the quasar that you see right here, being so bright and so exceptionally strong in luminosity that it actually starts illuminating the space nearby, and we can then detect those reflections. We can kind of start seeing the tiny reflections coming off the gas that is between those galaxies. And so this is exactly what this image here is showing us. It's showing us the reflections from this intergalactic dust, with galaxies being these tiny spots in the middle of pretty much every one of these dust formations. And you can sort of see how all of this connects everything together. So this is literally the first ever image of the so-called cosmic web. And this image is showing us what we've known all along, that the galaxies are connected with the galactic filaments, and they all form this dust web or cosmic web, stretching millions and millions of light years across. These are actually some of the largest structures in the universe, forming tunnels, or I guess forming very long webs stretching for hundreds of millions of light years across. And although previously it was basically a theoretical concept that we kind of suspected existed, we now have a definitive proof, and in the future I'm sure we'll be able to use a very similar technique to discover other filaments out there that are even more visible and possibly create even better pictures. And just like the models predicted, the most active galaxies were very likely the ones that were fed the most by this cosmic web. In other words, most of the material in these very active galaxies came from inside the cosmic web, and the amount of gas around these very active galaxies was the highest. So here, by looking at the most active galaxies in this image and also some of the hotspots in the image, it becomes quite apparent that the filament or the cosmic web is responsible for feeding these galaxies. And essentially most of the materials that creates these stars in these galaxies and of course powers the black holes in these galaxies comes from the outside of the galaxies through this cosmic web. So it's kind of like this feeding tunnel that siphons the material into the galaxy from the outside, and that's probably how a lot of things in our own Milky Way work as well. As a matter of fact, there are a lot of suggestions that Milky Way is connected to the nearby galaxies, Large Magellanic Cloud and Small Magellanic Cloud, and there's going to be a video where I explain to you how we know this. But at the same time, we don't really have any visual proof of the connection of the Milky Way with the Andromeda, but theoretically they are also connected through these cosmic webs. Here's the problem though, these cosmic webs are really difficult to see. And the scientists in this paper were actually really lucky. They got to use one of the most powerful telescopes out there, the European Southern Observatory telescope that you see right here, and because of this they were able to find just the right region of the night sky and also just the right collection of galaxies that was active enough to illuminate the nearby hydrogen. But nevertheless, seeing this is extremely difficult, simply because the hydrogen that we see here is just very dim. It's almost invisible. As a matter of fact, the scientists believe that this is just a very small part of the entire cosmic web that's technically here. We're only seeing a tiny part of the entire web in this region, and in reality it's probably a lot more pronounced and a lot thicker than what appears to be in this image. And because galaxies like the Milky Way and the Andromeda are just not really bright enough to illuminate hydrogen nearby, we're probably never really going to see this until we develop new techniques. But in order for us to get a better image of all of this, or possibly even the image of nearby cosmic web, we would have to use some sort of a UV telescope, and more specifically UV telescope in space. Unfortunately right now the only active UV telescope is this telescope right here, AstroSat from India, but I'm not entirely sure how good its telescopic lens is, so we're not really sure if it's going to be possible to use this to image the nearby space. However, I'm sure some of the scientists in the future will probably try to use it, and we might end up with a much better picture than this. In other words, we might be able to picture the nearby space close to the Milky Way galaxy and thus see the cosmic web that connects our galaxy to the Andromeda and to everything else. But for now, that's really it. It's definitely a really awesome picture because it finally proves that cosmic web is out there, and at the same time proves a lot of our theoretical concepts as well. In the future though, we'll probably get a much better one, and hopefully sometime in the next few years. Hello wonderful person, this is Anton, and in this video we're going to be talking about another discovery coming from the galaxy that we live in, the Milky Way. In a very recent discovery, the scientists actually found out that apparently we were kind of wrong about the mass of our own galaxy. And that's of course a little bit surprising because that's kind of like not knowing the total mass of your own home. Now, in their defense though, it's actually a lot more difficult to try to measure the mass of our own galaxy than it is to measure the mass of nearby galaxies, because basically we are somewhere right here in the middle and we're trying to observe the entire galaxy without really leaving it at all, and that's very, very challenging. Now, for the longest time we actually thought that our galaxy was a lot less massive, but turns out it's a lot more massive than we knew. Now, it doesn't mean that there's more stars. It actually doesn't mean that there's more visible mass. It's not the so-called baryonic matter we're talking about. We're talking about other mass. The invisible mass, the dark matter. The elusive dark matter that we still haven't really discovered anywhere, but we know that it's there because we see the effects. And so the scientists behind this study that you can actually find in the description below did something really interesting. They essentially used the so-called globular clusters, which is essentially the very large collections of stars, like for example this one right here, NGC 6441. So these globular clusters are relatively easy to see, and also because of this, it's relatively easy to measure their velocity. And the scientists behind this paper used the data from the Gaia Observatory that has been collecting data on billions of stars in our neighborhood and creating the three-dimensional map of nearby space around us. And this is actually some of the data that has been used to predict what's going to happen in the future. That's how accurate this data is. And it of course includes some globular clusters near us, and so they used 34 of these clusters discovered by Gaia and tracked by Gaia, but also, just to confirm their results, used 12 more globular clusters also observed and tracked by Hubble telescope. So they made sure that their data was very, very accurate. And what they discovered was that, well, basically it turns out that these globular clusters were moving faster than we expected. And because they were moving faster than we expected, but still staying within the galaxy, basically something was actually holding them within the galaxy, that only meant one thing. There's more dark matter in our galaxy than we originally believed. So they had to recalculate the assumption for the dark matter to discover a new value for the mass of the entire Milky Way. And this value now stands at approximately 1.5 trillion masses of the Sun. Or potentially even higher at 2.3 trillion. That was their highest value that they've discovered so far. Now, all of this was based on the fact that when they calculated the speeds of globular clusters, they were moving at around 206 kilometers per second, way faster than expected. Meaning that our own galaxy is at least 2 to 3 times more massive than we originally thought, but more interestingly, Milky Way also seems to be potentially twice as massive as the Andromeda galaxy. And of course, for the longest time, we believed that this was the opposite. We actually thought the Andromeda Galaxy was twice more massive than the Milky Way. But this recent discovery suggests almost the opposite. In other words, we are currently, it seems at least, the most massive galaxy in the local region. Milky Way is literally the center of the local region, at least for now, until we discover something completely different. And I guess it's kind of fair to ask, so why is it that we keep changing these values all the time? How can we go from thinking that Andromeda was twice as massive, but now we think it's the opposite? Well, it's because of the so-called dark matter. The visible matter is actually very easy to see. Obviously, stars are relatively bright, so it's relatively easy to statistically estimate how many of them there are in the Milky Way and in the Andromeda. But this stuff is invisible. This stuff doesn't interact with anything. We don't really know how much of dark matter there is, or if it's even real. And we only see the effects, and the effects are quite obvious. And these effects tell us that, well, for the most part, in the Milky Way there seems to be more of this invisible stuff, whereas in the Andromeda there seems to be less. So the total mass of the Andromeda is thus twice less than the Milky Way. And this is actually good news, because essentially it means that we're discovering these new techniques that allow us to study the universe and space around us with a lot more accuracy than before. Using things like Gaia telescope, for example, allows us to very accurately predict motions of nearby objects. At the same time, telescopes like Hubble that have been working for decades and decades are still discovering new things even today. And with 2019 being a pretty good year for space discoveries so far, I think there's definitely going to be a lot more things that we're going to find out about the universe in the next few months. So overall, I honestly actually really love these discoveries, because it kind of redefines our understanding of everything. The science is evolving, the science is changing, and so is our knowledge, because you can't just always believe in the same thing. We're still pretty young at trying to understand the world around us, and we can't just settle for one thing. We have to always try to reinvent ourselves, and also try to change the way that we learn as well. So because the science is doing just that, I'm actually very happy at making these videos and always correcting, well, I guess you can call it mistakes, but not really, because we just didn't really know better. Yeah, of course, initially we thought that Milky Way was not as massive and Andromeda was the giant nearby, but now we think it's the opposite. And that kind of makes us learn about everything.
Hello wonderful person, this is Anton, and in this video we're going to be talking about our own galaxy, the Milky Way, and a new study that seems to actually teach us that we were once again wrong about something in our own galaxy. Who would have guessed, right? So when it comes to galaxies, and specifically our own Milky Way, we're kind of cursed in the sense that we can't really see our own galaxy from the outside, because we are inside of it. So it's sort of like seeing the entire country of the United States by essentially standing on a single spot somewhere in Washington, D.C. It will be quite difficult, quite impossible as a matter of fact. And that's kind of what we have to deal with here. But it turns out that we can still learn about the shape of our own Milky Way, and also about a lot of things happening here by looking hard enough. And this is what basically this video is about. This is a wrong assumption about the Milky Way. It's not really straight and flat like we assumed. The study by Xiaodiang Cheng and Xu Wang and the team from the Chinese Academy of Sciences used a very interesting technique using what's known as the Cepheid variables to try to see what kind of a shape our own galaxy might have. Okay, so this is kind of what they did. So first of all, what is a Cepheid variable? Cepheid variable is a type of a star that basically changes its brightness very periodically with a predictable pattern. It goes bright, dim, with a certain period. And you can use this period and also the maximum brightness to actually estimate distances. This is what we usually refer to as a candle. It's essentially a way for us to measure distances based on the brightness of an object. These are very accurate, and they've been studied for many years. So we do have a really good sort of understanding of how this works. They then took a look at several Cepheid variables around our galaxy. And this is actually us right here. And what they realized is that, well, it seems that some of these stars are in a location where it doesn't really make our galaxy entirely flat. They essentially realized that our galaxy seems to have this type of shape, a kind of a folded, bent disk. And this is, although very interesting and somewhat unusual, is not unexpected. As a matter of fact, there are quite a lot of galaxies we've discovered so far that do have a somewhat folded and somewhat interesting shape. Here's actually one of such galaxies. This is a galaxy known as ESO 510 G13, and as you can see, it does have this very visible fold that we believe our own Milky Way has as well. We just can't seem to see it because we're literally looking at it from the inside of the galaxy, so it's very difficult to see. But this particular study, as long as it's all correct and as long as it can be confirmed by other scientists, suggests that this is the shape of our galaxy. It's not a flat disk. It's a disk that's kind of folded and bent. In other words, what we have here is not entirely correct. This is the Milky Way in space engine, at least as of our assumption in 2018. But in 2019, we might have to change this to make it more warped. And so in reality, if we were to compare this to the other galaxy that we know very well, this is what the Milky Way probably looks like. This is the ESO 510 G13, but it's essentially a somewhat warped, very unusual looking pancake. Now, I guess the next question is, so why did this happen? And how did this happen? And the first assumption that one may make is that it's probably from interaction with another galaxy, but turns out that it's not necessarily true. As a matter of fact, it's probably because our own galaxy has a tremendously large mass in the middle, in the center. So in other words, the disk that you could imagine when you're thinking about galaxies has a very massive part in the center, while the sides are not as massive. And so when this disk starts spinning and turning around, the mass in the middle starts warping the sides a little bit, and they end up looking just like the picture you saw right here. And so that's the current assumption of what may have happened to the Milky Way. Although that's still a very early assumption because this study literally came out only a few weeks ago. Now we still need to follow up on this, make sure that we actually have the data correct, and then try to look at a few more of these warped galaxies to see if we can explain the warp in some other way. But for now, I guess the assumption is that this warping is from the fact that our galaxy has a very massive central part that has caused the other parts of the galaxy, the side parts of the galaxy, to kind of bend a little, to warp a little, and to become a little bit misshaped. But I guess what's really cool about this discovery is that this basically puts Milky Way into the club of somewhat rare warped galaxies. We've only discovered about 20 of these so far, and they're a lot more rare than the super flat galaxies. And so, in that sense, it makes Milky Way even more rare, more exciting to live in some sense, a pretty interesting, mysterious place that hopefully one day we'll learn more about.
Hello wonderful person, this is Anton, and in this video we're going to be talking about a relatively recent discovery of how truly large and tremendously big our galaxy is. This new analysis finally establishes the size of our galaxy to the extent we've never really thought possible. It's actually kind of interesting that if you were to Google up size of the Milky Way, this is the result you get. Roughly around 52,000 or 53,000 light years in radius. And the same type of information will be also found in many different textbooks, and I guess in some sense it is true, but this is actually a slightly outdated version of what the galaxy is like. The cross-section here, as you can see, shows us the location of the sun, and then the galaxy kind of ends right here. In other words, all of this refers to the very easily visible part of the galaxy and ignores a large part of the galaxy known as the galactic halo that is truly incredibly large in comparison to what we see here. The best example of a typical galactic halo comes from the images of the largest galaxy we've ever discovered, IC 1101. Here, technically, I guess you can maybe call this a galaxy, but in reality the halo extends to dramatic levels. This makes this galaxy 2 million light years across and the biggest example of what's known as an elliptical galaxy with a super huge halo around it. And it's slightly easier to see it in this black and white image where you can see that the visible galaxy is definitely large, but the halo is even larger. And so our galaxy is no exception. It also has a very large halo around it, but it's obviously super difficult to see. As a matter of fact, the paper that I posted in the description below that talks about the new measurements of our size of our galaxy specifically states that it's actually kind of as if you're looking at the size of the forest by measuring everything from within, from inside the forest. It's a very difficult task, it's super difficult to do, but they managed to do it really well. And so the team behind this particular paper from Japan used the Subaru telescope with extremely sensitive cameras to try to discover the true sheer size of our galaxy. Now this is what they looked for. They looked for really bright stars and also really bright globular clusters with various variable stars, such as, for example, RR Lyra variables that you can kind of see sparkling right there in the image. These really bright blue stars sparkle, or technically change luminosity, very periodically, and by knowing their periods and how luminosity changes, we can very accurately determine the distance to those objects. So they've discovered several hundred of these stars, and they looked at a tremendous amount of various globular clusters as well, and you can actually see there's quite a lot of them hiding right there in the halo of our galaxy. And by looking at all of these globular clusters and all of these RR Lyra stars, they discovered something unusual. Now normally you expect the so-called density of dust and stars to slowly decrease as you move away from the center of the galaxy. But there's a distance at which suddenly there's a instant drop in both density and the number of stars. And they've discovered where this happens. And it happens at a really far away distance. I'm actually going to try to help you visualize this by moving to that distance right now. The sudden drop in stars and in globular clusters happens roughly at a distance of about 522,000 light years away from the center. That's about 20 times as far away as Earth and the Sun are from the center. So that's basically somewhere right here. And that is really far. So this literally is the so-called limit of the galactic halo for the Milky Way galaxy. This makes our galaxy tremendously large compared to what we believed originally and what we normally think of when we think of a galaxy and its size. And what's even more interesting is that this actually makes our galaxy almost as large as the Andromeda. The biggest neighbor that we have, the Andromeda galaxy, at a distance of roughly around 2.5 million light years away from us, is just a little bit more in terms of size of its halo. The size of this galaxy is about 534,000, whereas the size of our galaxy is 522,000 light years. And also in one of the previous videos I've discussed how we may have underestimated the mass of our own galaxy, so it looks like the Milky Way is slightly smaller but more massive overall, which is actually a huge surprise when you think about it. And here I tried to recreate all of this in Universe Sandbox by using the original model of Sagittarius A star and then placing a bunch of objects that I called moons basically, each of which represents different stars and different globular clusters, just to give you an idea of how large the halo really is. So here, if we zoom into it, it's actually surprisingly a black hole. I guess I miscalculated the mass there, but this roughly gives you an idea of how tremendously large our galaxy really is. This halo is really big. There are billions of stars here. There are a lot of masses of the stars. There's obviously a lot of things like black holes. There's probably also a lot of dark matter hiding here. And we found at least 150 globular clusters in the halo of the galaxy, meaning that it's basically a tremendously massive place. But it is more dim, it's more difficult to see, so that's why the typical textbook will never really show you this. It will never really display a galaxy as something like this. It will probably just show you the typical galaxy shape that we're used to. And the other thing they discovered that's sort of interesting is that the vast majority of all of these objects that I seem to be losing now because they came too close to the galaxy is actually really old. So instead, let's use a real globular cluster from a space engine in the halo of our galaxy. So this right here has a lot of really ancient stars. Pretty much all of the stars here are at least 12 billion years old. And there's a lot of very ancient systems with a lot of ancient planets and probably a lot of ancient mysteries as well. All of these are remnants of really old events that happened in the creation of our own galaxy, probably when the smaller galaxies collided together, eventually forming the Milky Way. So all of these collisions happened approximately 12 billion years ago, and the results or the leftovers from these collisions stayed as the halo in our galaxy, while most major stars came closer and closer to the center, forming what we know as a Milky Way spiral galaxy that we have today. And so all of this suggests that around 12 billion years ago, several smaller galaxies very likely combined together. And this of course also suggests that at some point Milky Way was probably much larger before the disk was created and before it solidified as the shape that we know today. It was very likely a much larger object with a lot of diffuse matter and a lot of other ancient stars orbiting around it. Now, on that note, that's really all I wanted to talk about in this video. It's definitely a really cool discovery, a very interesting redefinition of the size of the galaxy, and most importantly, it will probably inspire other scientists to look around and discover some other things that we kind of take for granted but are probably incorrect. Hello wonderful person, this is Anton, and in this video we're going to be talking about a discovery of more unusual galaxies that seem to possess no dark matter or very little dark matter for that matter. No pun intended. So let's start right here. This is a galaxy very close to the Milky Way. This is what's known as an ultra-diffuse galaxy. Basically a galaxy that seems to possess very few visible matter. It has some stars but not a lot. Compared to the Milky Way galaxy that has a lot of stars, it's very difficult to see these diffuse galaxies. But the thing is, we've been discovering more and more of them as our telescopes get better. We've discovered quite a lot of them near the Milky Way, and we also keep discovering them very close to other large galaxies. But for the most part, even though there are not a lot of stars here, they do seem to have a lot of matter. And we believe it's of course the so-called dark matter, the invisible matter that seems to keep things together in the universe. Now, because this galaxy is very dim and very difficult to see, if you have a very powerful telescope, even then you're going to have trouble finding it. It's going to be practically invisible in the night skies unless you have basically an equivalent to Hubble telescope. Which is why discovering more of these galaxies is kind of difficult. But we've been doing a pretty good job at finding more and more of them out there in the universe. But the one that kind of became controversial, about which we've talked about, I think it was last year, was this right here. You're about to see it. It's known as, let me just read this, NGC 1052 DF2. There were actually two galaxies very close to each other. One was DF2 and one was DF4. And DF stands for Dragonfly, which was the telescope used to discover this. And it's coming in the view in a few seconds. But basically, the reason why this galaxy was somewhat important a few years ago is because it seemed to possess very little dark matter. In other words, it was very difficult to see, first of all, but even the stars that were here were the majority of the mass. Now, pretty much within a month after the publication of the paper that talked about this ultra-diffuse galaxy, another paper tried to disprove their finding by basically suggesting that the galaxy was much closer and thus it did have quite a lot of dark matter, so there was nothing weird here. But then follow-up studies discovered that NGC 1052 DF2 was indeed a strange galaxy. It was, as initially suggested, a galaxy with very little dark matter. And this is basically science at work. Someone proposes something, other people try to prove them wrong, and then eventually we come to a consensus whether the person was right or wrong. In this case, it seems that the initial discovery of this being a low dark matter galaxy are kind of correct. And it was only a matter of time before more such galaxies were discovered. Now, out of 324 dwarf galaxies within about 500 million light years away from Earth, the scientists behind the paper that you can find in the description below discovered that at least 19 of them, and you can see the names of some of them right here, seem to possess very little dark matter or a lot less than they should. In other words, these are once again dark matter deficient galaxies. But unlike the initial study on NGC 1052 DF2, the study done here was actually using a very different way of analyzing all of this. And this is also the same technique that was able to finally prove that this has very little dark matter. The two techniques used are essentially as follows. So for the first technique, the scientists used the speed of so-called globular clusters. Here's one, for example. The globular clusters, as you can see, are the collection of stars, and usually these are pretty easy to see from even really far away distances. Most galaxies have a few hundred of them at least, and usually by measuring the speed of globular clusters across the galaxy, you can then sort of estimate the so-called galactic curve or the galactic velocity curve of a typical galaxy. So, in a nutshell, let's say we want to find out how fast the stars spin in this galaxy. From a distance it's going to be really hard to do because we can't really see individual stars, but we can still see the globular clusters. And so by looking at, let's just say, I don't know, 10 or 20 of them, We can then estimate the speed with which all of these stars spin, and using the galactic velocity curve, we can then estimate the total mass of the galaxy. And so let's just say the velocity of the galaxy is really high, so stars here spin really fast. While at the same time, there's just not enough stars here to create this velocity. This would suggest that something is creating more mass in the galaxy, and that something has to be dark matter. This is basically what we're seeing across pretty much every galaxy in the universe. While at the same time, if suddenly the velocity is much lower, if the stars are really not moving that fast, we can kind of assume that there's just not enough mass here, and so most of the mass in this galaxy comes from visible matter, from the so-called baryonic matter. So in other words, here, this galaxy seems to be lacking dark matter. And by looking at the speed of globular clusters, we can make this estimate. So this is what was done for the initial observations of NGC 1052 DF2, the galaxy that created so much controversy in the beginning. But with the discovery of these other 19 galaxies, we used a slightly different technique. We used what's known as the hydrogen rotation curves. In other words, instead of looking at the starlight, we were looking at the hydrogen gas itself. And we can usually do this because hydrogen has a tendency to emit quite a lot of specific frequency. This is actually known as the 21 centimeter line, also known as the hydrogen line. And what's really interesting about this line, or this hydrogen emission spectrum, is that it's equivalent to about 1.4 megahertz, 1.42 more specifically. And you can technically actually detect this if you have an antenna at home that's powerful enough to receive this frequency. Just to give you a comparison, the Wi-Fi in your house probably uses 2.4 gigahertz or maybe 5 gigahertz, so it's not that different from an antenna that you would use for a router, for example. It's a little bit longer. And the reason why it's called 21 centimeter or basically 1.4 gigahertz line is because of the way that the electron inside hydrogen acts and how whenever it sort of flips around, basically when it changes its spin, it actually emits the light or the actual frequency of exactly 1.42 gigahertz. So that's kind of in a nutshell how all of this works and why hydrogen emits this specific frequency. And so all of the hydrogen in our galaxy and all of the hydrogen in the universe produces the exactly same light. So if you have for example, a radio tuner at home that's capable of receiving this frequency, and if you were to sort of wave your antenna around the night skies, you might be able to actually detect this. I've done this with a very simple antenna that I bought on Amazon, although without creating a somewhat complicated mapping algorithm, it would not be particularly useful. It just basically shows you that, yeah, there's hydrogen somewhere over there, but it will be difficult to detect where. But anyway, so this is how we can detect hydrogen everywhere in the universe. And by looking at this specific line, this emission line, the scientists were able to estimate the total velocity of those 19 different dwarf galaxies. And just as the title suggests, it seems that they too are missing dark matter because the hydrogen is moving a little bit slower than they should be moving, and suggesting that basically there's a lot more visible mass than there should be, not enough dark matter. All of the 19 discovered galaxies seem to be outliers of the assumption of what we think a typical galaxy should have. And even though they don't actually have just visible matter, in other words, they're not completely void of dark matter, they do seem to have a lot less than they should. So as an example, in this galaxy here, we expect about 2% of mass to be stars and visible matter and hydrogen, whereas probably about 98% is going to be dark matter. This is sort of typical for a dwarf galaxy or many dwarf galaxies we have observed in the last few decades. However, in the galaxies discovered, such as the ones you see right here on the list, the percentage is very different. The calculations suggest that approximately 27% is visible matter, the rest is dark matter. So even though dark matter is still the majority of the galaxy, it's far from what we would expect from other smaller dwarf galaxies. And unfortunately right now there is no good explanation for what's happening. As a matter of fact, it does create a lot of problems for modern physics. We don't really know how these unusual galaxies could possibly form. One explanation is that maybe, and let's actually try to simulate this, maybe these galaxies moved closer to a larger galaxy and some of their or most of their dark matter was stolen somehow. In other words, maybe they experienced a tidal disruption. But the thing is, 5 of those galaxies were in a region completely void of other galaxies. They were in empty parts of the universe, and that wouldn't really explain how they lost the dark matter and how they became the way they are. So in that sense, we're not entirely sure how to explain their existence just yet. At the same time, because we're talking about hydrogen gas, there are other things that can technically accelerate hydrogen. For example, if a typical dwarf galaxy suddenly experiences a supernova or several supernovae, the energy produced here would be enough to suddenly accelerate the gas. So supernovae are technically responsible for accelerating gas across the galaxy, and if those smaller galaxies experienced a lot of supernova, then this might explain why the gas is moving so fast. And another explanation involves the angle from which we're observing these galaxies. So like, for example, if we're looking at this from the top, the velocity here will be much larger, but if we're looking at it from an angle, this apparent velocity will suddenly be much lower. So this could be one of the possible explanations. We need to kind of confirm the angle of observation and try to find out if we're looking at these from the correct angle. But anyway, so we don't really know exactly what's happening in those 19 unusual galaxies, but they might be just really strange and for some reason lack dark matter. This unfortunately creates a lot of problems for modern physics, but at the same time creates a lot of opportunities for new studies to either prove this or disprove it in some way. Hello wonderful person, this is Anton, and in this video we're going to be talking about a new discovery about our own galaxy, the Milky Way. And more specifically, we're going to be talking about the galactic disk of the Milky Way and its age. So when it comes to studying space, one of the most difficult parts is actually studying our own galaxy. Because of our location within the galaxy, it's very difficult for us to see a lot of things in it. We can only mostly imply the things about our own galaxy by looking out there and trying to find analogs or similar galaxies that could somehow resemble the Milky Way. For example, by thoroughly studying certain parameters of the Milky Way galaxy, we not so long ago discovered that our own galaxy resembles something that looks like this. It's not really that flat. It seems to have a bit of a curl or a bit of a warp. And this is based on a galaxy we've observed somewhere out there, and if you were to look at the Milky Way, it might look something like this. So this is what we believe our galaxy looks like. We've also not so long ago discovered these unusual Fermi bubbles that you see here. And these things here resemble bubbles that usually form around active galaxies, such as for example nearby Seiffert galaxies. So in that sense, this resembles what we've seen around the nearby galaxy known as Centaurus A. And so with time we're learning more and more about the shape, the structure, the composition, and now the age of the Milky Way. And so the recent study that used the Australian Astro 3D, which is this excellent project that you can check out in the description below, essentially allowed us to investigate the age of the so-called thick disk. Now, what exactly is the thick disk? Well, a typical spiral galaxy, even though it looks like it just has this one spiral disk, in reality has 2 disks on the inside. In a nutshell, it sort of looks like this. So we have our bulge in the middle, that's the most visible part of a galaxy. We have the thick disk, which is the larger and also much older part. And then we have the thin disk, that's usually much younger. And then there's a bunch of globular clusters all over, and the so-called halo. This is probably the simplest way of imagining a typical galaxy similar to the one where we live. And so when the scientists behind the study applied astroseismology to literally thousands and thousands of stars that were discovered as part of the Kepler-2 project, they realized 2 things. One is that there was a slight miscalculation with the previous age of the disk, and 2 is that, well, it seems that now we have a relatively accurate age of the thick disk of the Milky Way, and this age has been found to be roughly around 10 billion years old, suggesting once again that the thicker region of the Milky Way here is at least 10 billion years old, and at the same time suggesting that the disk formed billions of years after the rest of the galaxy. So here we have to start looking at the galaxy as forming in different parts. It seems that approximately 12.8 billion years ago, this part, the bulge, was born, most likely through the galactic collision of various small galaxies that existed about 1 billion years after the creation of the universe. Following this, and here we can actually accelerate time to maybe possibly form this bulge. Okay, this is not as thick as I wanted it to be, but I guess it will have to do for now. For almost 3 billion years, the galaxy very likely just looked like this. In other words, it resembled a typical elliptical galaxy, somewhat similar to what we can create here in Universe Sandbox. So this elliptical galaxy, or this bulge, the galactic bulge of the Milky Way, is still there, and it contains some of the oldest stars in our galaxy. As a matter of fact, we've discovered stars that even sort of break the rules of the universe. There was even one star discovered a few years ago that seemed to have been even older than the universe, although there was a slight miscalculation and a huge range of error, so it's definitely not going to be that old. But nevertheless, all of these stars today are at least 13 billion years old, and many of them are still there and are still kind of kicking. Then, within the next 3 billion years, something else happened. It's very likely that other galaxies started to collide with this bulge and eventually formed what seems to be the beginnings of the thick disk. All of this happened around 10 billion years ago, and then for the next billion years, the galaxy still sort of maintained a relatively disk-like but not very flat shape. It probably resembled something like this. Although for all we know, it could have also been a lot more similar to what is known as the Sombrero Galaxy right here. In either way though, we're not really sure yet because we haven't analyzed how all of this changed over time. We only know how old these stars are. And then about 8.8 billion years ago, or roughly around 1.2 billion years after the creation of the thick disk, that's when the final part of the galaxy was born, the thin disk. And this may have been from either another collision or the sudden addition of gas from somewhere else. And then eventually, over time, the disk stabilized and began resembling a typical spiral galaxy that we kind of see everywhere around us now. So unfortunately, we don't really have any more detail about this. We just know that the thick disk is roughly around 10 billion years old. But hopefully one day we'll be able to reconstruct all of this in terms of the actual progression. It'd be interesting to find out what happened first, how certain parts of the galaxy, like for example the spiral arms, were created, and how all of this eventually ended up in the shape that we have today. But it's not going to happen anytime soon because we'll need a lot more analysis and a lot more observation of various parts of the galaxy before we can discover something else that can advance our knowledge of morphology of the Milky Way. At the same time, this discovery presents the Milky Way galaxy as an extremely ancient galaxy. Just the fact that the thick disk was developed so many years ago, 10 billion years ago, is a little bit mind-blowing. And just to give you a bit of a perspective, our planet Earth and our solar system is only about 4.5 billion years old, meaning that it's not even half as old. So our galaxy was already established and had a very similar and very familiar shape for at least 5 billion years before our planet Earth was even created, suggesting once again that the Milky Way is one of the more ancient galaxies out there. Hello wonderful person, this is Anton, and in this video we're going to be talking about the origins of the Milky Way and discuss a little bit more about what happened to our galaxy about 10 billion years ago. So in some of the previous videos, actually in a lot of videos, we've discussed the origin of, for example, our solar system, also how the Earth-Moon system was created when an object known as Theia collided with Earth, but we never really discussed how our galaxy was made. And so today I wanted to discuss a little bit more about this recent study that very thoroughly analyzed the origin of the Milky Way. And specifically the collision, the very large collision that it received around 10 billion years ago. This paper from Nature magazine that you can find in the description below talks about what happened to the sort of primordial Milky Way when it collided with another galaxy known as Gaia Enceladus. Here is a very rough summary that was created by Gabriel Perez-Diaz that shows you that about 10 billion years ago the galaxies collided and the present-day galaxy was created as a result of this. But how exactly do we know all of this, and also what exactly may have happened? Now it's very difficult to answer the second question because, well, we're still kind of early in our understanding of galactic collisions. We have a lot of simulations, like for example here's one from Universe Sandbox where you can see two relatively different galaxies colliding, and we can actually even see what happens as a result. And we've also seen a lot of galactic collisions out there with, for example, Hubble telescope, but in most cases, our actual understanding of the process is still only limited to simulations like this one you see on the screen. So in some sense, we do understand it, but in most other senses, it's still kind of new to us. We do, however, know that the galactic collisions started happening almost immediately. This is the earliest such collision we've detected only a few months ago, and this happened only a few million years after the creation of galaxies. And this one here was known as B1465666. And the actual image that was discovered only a few months ago from when I'm making this video looked something like this. And this was quite astounding in that it seems that galactic collisions started happening basically almost right away. But our own galaxy, our beautiful Milky Way, did not receive these large collisions until only about 3 billion years after its existence. As a matter of fact, it seems that the early Milky Way galaxy was relatively calm. It may have absorbed some of the galaxies, some of the smaller galaxies nearby, so basically dwarf galaxies that were circling around it, and it did increase its mass a little bit, but for the first 3 billion years it was just a typical disk galaxy, not really a spiral yet, and it was absorbing a lot of mass, but also creating a lot of stars. And today we know that eventually the Milky Way will collide with the Andromeda Galaxy. This is going to be probably the largest collision our galaxy will ever experience. And eventually these two will, well, first of all, they'll do something similar to what you see in this simulation here. They'll basically destroy each other in a sense, but then eventually combine into a single galaxy that is going to be ridiculously massive, because as you can see, there's another third object there, that's the Triangulum galaxy, that will also join them at some point as well. So this will be the sort of ultimate galactic collision in our own neighborhood. But today we know that, well, our galaxy definitely had collisions before as well, and the first such large collision very likely happened 10 billion years ago. Now, the simulations for it are still kind of not really that accurate, but our understanding of what happened and also what happened to the galaxy afterwards is quite accurate. And all of this is based on the analysis from the beautiful Gaia telescope that in the last few years was able to extremely accurately map nearby stars, millions of nearby stars, within about 6,500 light years away from our system. And we now have very accurate location, very accurate motion, and also very accurate distance to those stars. And because of this, not only can we now predict what's going to happen to the galaxy, we can also look back in time and see what caused certain features of the galaxy. And this is exactly what this particular paper did. They looked at the nearby stars and realized that of all of the stars they studied, there was one group of stars that they referred to as the red type that had very high metallicity, basically very high content of non-hydrogen, and another group that they referred to as the blue type that had very low metallicity. And they both had relatively different ages, relatively different compositions, but together these two groups may have come from two different places. And they realized that the blue, non-metal rich stars probably came from a completely different galaxy a long time ago, roughly around 10 billion years ago. They also realized that both of these galaxies were roughly around 3 billion years when this happened. Both of them were creating a lot of stars, and as a result of this collision, they actually increased the amount of stars that was being created in the Milky Way dramatically. So Milky Way kind of became a very active galaxy for a little bit, and then within about 3 to 4 billion years after the collision, Milky Way settled into its shape that we have today and remained the same way since. In other words, this shape here was very likely established about 6 billion years ago and hasn't really changed much, except for occasional smaller collision with dwarf galaxies that did transform its shape a little bit, like for example giving it the ripples about which I've talked about in one of the previous videos. I think it's somewhere above my head right now. And although the initial star production right after the collision was probably really high, we don't really know how many stars, but there were a lot of stars that were being created because all of this dust that you see mixing here then had a chance to combine into larger stars, larger objects and so on. Following this, after about 2 to 3 billion years, the actual star creation sort of settled and has not changed since. So in the last 6 billion years, it's very likely that the Milky Way galaxy has been producing roughly around, well, in terms of masses, about 1.3 to 1.6 masses of the Sun per year. And this has not changed for a really long time and will not change until the collision with the Andromeda Galaxy. But what's unusual about this particular collision is that it took so long for Milky Way to get its first major collision. We know that it received smaller collisions, but this major collision took 3 billion years. This suggests that it's very likely the Milky Way galaxy was in a relatively remote location with no other larger galaxy in its vicinity. Because today we know that galactic collisions happen very frequently, there's a lot of them, and we even have a very unusual term for some of the galaxies that collide with other galaxies. We call them galactic cannibals, basically because they eat up other galaxies. And today Milky Way is seen as such cannibal because it's absorbed a lot of galaxies, smaller galaxies, over time, with the Gaia Enceladus galaxy being the biggest such object for another 2.5 to maybe 3 billion years, until Andromeda decides to combine with ours. Now, it's not really clear just yet what's going to happen to Milky Way after the Andromeda collision, but today we believe that they're probably going to become sort of like a mixture or a hybrid and turn into a somewhat shapeless, what's known as an elliptical galaxy, basically a galaxy that doesn't really have a disk anymore. And that's because both galaxies are relatively similar in mass and in size, so neither one of them is a cannibal anymore, they're just combining into one. But although it's somewhat difficult for us to predict what's going to happen in a few billion years, we can definitely try to analyze what has already happened. And this is why Gaia telescope allows us to do all of this with so much precision now. And just to finish all of this, I actually wanted to try to recreate this collision or something similar to this collision using Universe Sandbox, because we do have these beautiful, very realistic looking galaxies in the simulation now. So here is the Milky Way, what it may have looked like approximately 10 billion years ago, and this is the galaxy that it's about to swallow, known as Gaia Enceladus. Now, I didn't really put them in the location that you saw in this image, mostly because we're not even sure if this is how it happened. We just know they collided. We don't really know what inclination they had to each other. We also don't really know how fast they were moving. We just know that it sort of happened. Once we have more data coming from Gaia, we'll be able to kind of go back in time and find out how exactly it happened. For now though, we're not really sure. Which is why our collision is going to be basically really simple. Two galaxies, one larger one smaller one, colliding with one another. Now, for this to be very accurate, we of course would need to have dark matter, but it's very difficult to simulate dark matter using a simple computer that I have at home, so we're just going to have visual representation of all of this. And so here, from this particular angle, we can kind of see that these galaxies maintain their shapes until the last moment right before the collision happened. And what's really interesting about this is that the stars that were present in both galaxies are still out there in our galaxy, and also we can discover them and we can study them in a lot more detail to try to find out what those galaxies were like before the collision. Some of these stars, specifically the red dwarfs, are still alive and well, and they still emit enough light for us to study them. And so here's the collision, and as you can see, the Milky Way cannibalized the smaller galaxy, absorbed it into itself, and I just saw the black holes accidentally leaving the system. So yeah, it looks like we destroyed the whole thing. And that's because I think the black holes here were a little bit too massive. I need to make them smaller. And unfortunately, even in the second simulation, my suspicion is that the black holes will probably not really play along. But anyway, you can see how beautiful all of this is. You can see how the larger galaxy is cannibalizing the smaller galaxy, basically absorbing all of the matter, and all of this will cause a tremendous explosion in star formation. And then we have this expulsion of some of the matter. This is based on the black hole interaction, which will be followed by the creation of a somewhat stable cylindrical shape that will then become the Milky Way as we know it today. In other words, this shape right here will be formed after about 3 to 4 billion years of stars just circling around, being destroyed, being created, and within about 3 to 4 billion years, it will stabilize into the shape that we know today. But in this particular simulation, it looks like creating a spiral galaxy did not go very well again. We may have failed yet again. Now, as you can see, it's not a very easy task. As a matter of fact, this is why we believe galaxies are not just a collection of stars and matter. Today we believe that there's a lot more other things involved, including of course dark matter, that will have contributed to the stability of the shape of the galaxy and also prevent the galaxy from doing this, from falling apart. So this present day shape of the Milky Way has definitely been formed and shaped by not just the interaction of matter, but also a very strong influence from other mysterious things like dark matter. And possibly without it, we would not even have anything that looked like this. Instead, it would look something similar to what I just created right here in Universe Sandbox. Anyway, on that note, check out the paper that I mentioned in the description below. It's a very interesting analysis of what may have happened to the Milky Way about 10 billion years ago. And in some of the future videos, we'll explore some other unusual things we've discovered about our galaxy that you may have not known before. Hello, wonderful person. This is Anton, and in this video, we're going to be talking about a possible solution to an old mystery. The mystery which relates to the potential formation of really massive galaxies, really huge galaxies, early in the creation of the universe. We never really knew how it was possible, and we also didn't really know where they came from. When it comes to discovering new galaxies and just kind of talking about the development of galaxies, we're still learning what's really happening out there. Now, one of the biggest mysteries in the last few years was that when looking at some of the more distant galaxies out there, the scientists discovered something really unusual. And as you can see here, we're currently looking at some of the really distant, really ancient galaxies. So what the scientists discovered is that for some reason, even about 1 billion or maybe 2 billion years after the creation of the universe, after the so-called Big Bang, there already were a lot of really massive and also really well-developed galaxies with a lot of stars, as many stars as our own Milky Way. Now, according to the current timeline of the creation and the evolution of the universe, the first stars only started to appear about a few 100 million years after the creation of the universe, and this is when the galaxies started to evolve as well, suggesting that in the first billion years or so, the actual galaxies were very simple. That's of course our assumption today. But when we look at those ancient galaxies, once in a while we'll see a fully developed, really massive galaxy that already exists about 1 billion or maybe 2 billion years after the creation of the universe. And the evolution and the existence of these galaxies is really difficult to explain. It's as if they suddenly appeared out of nowhere and appeared really quickly. And when we looked around the night skies, we couldn't really find any way for these galaxies to form. So this was always a mystery and we could never really explain it. And we've actually seen quite a few of these well-established ancient galaxies that existed about 1 billion to maybe 2 billion years after the creation of the universe. And so it was with this recent paper that we're actually kind of now able to explain how all of this may have happened. The paper that you can find in the description below talks about a discovery of what appears to be the signs of a very massive galaxy similar to the Milky Way in size being formed approximately 12.5 billion years ago. That's about just over 1 billion years after the creation of the universe. But what's interesting is that we're not really seeing the galaxy itself. As a matter of fact, what we're seeing is more or less this. We're basically just looking at gas. But today we have telescopes that can actually see through gas and even see what happens behind this gas. And so by using the very powerful ALMA telescope and by focusing on just a specific part of the sky and also by using a very specific frequency, the scientists were able to pierce through this gas and see behind it. Now, first of all, cosmic dust is usually a bit of a problem when it comes to looking at distant objects. For example, one of the reasons why it's so difficult for us to see the center of our own galaxy or to actually see behind the center of our galaxy and thus investigate the dark side of our galaxy is because the dust is actually hiding it. So here, in the visible light, this is what the Milky Way center looks like. But if we were to look at this in other frequencies, like for example the infrared, we would start seeing different things. And once you get to the actual radio frequencies, you'll start noticing things that didn't really exist there before. Because for the most part, radio waves can easily go through the space dust and thus allow us to see what's hiding behind this gas. And as you can see here from the radio telescope known as GLEAM, which is in Australia, there are a few things in the middle of our own Milky Way that we now can see that were not visible to us before. So by using a similar principle and by using radio frequencies, we can then look into the distant parts of our galaxy and see behind this ancient gas as well. And so by doing this, the scientists behind this paper discovered this unusual eerie glow, which resembled almost like a ghost-like formation in the middle of empty space. This was a very massive and very powerful event that was hidden by a lot of dust. And having run a thorough analysis on what they were looking at, the scientists behind this paper realized that this was an extremely massive and an extremely powerful galaxy that's being created, but is also hidden by the dust, so we don't actually see it. In other words, a very powerful event was taking place. A lot of new stars are being generated, possibly hundreds of times faster than here in the Milky Way. And all of this is happening hidden behind this really large primordial dust that was still there in the early universe. And according to the scientists behind this paper, when they saw that this galaxy was actually invisible at any other wavelengths, except for that one wavelength they looked at, they got really excited. It really meant that this was probably a really faraway galaxy being formed, but is just hidden behind this cloud. And the glow that they were observing was formed by the formation of millions and millions and billions and trillions of stars that were forming right there at that moment. In other words, what this really kind of explains to us is that these ancient massive galaxies were probably formed behind this dust cloud and eventually absorbed all of this dust into themselves and then became visible to us. In other words, even though we might only see something like this if we were to look at it in a powerful telescope, behind all of this dust we would probably discover something similar to this. A very powerful starburst galaxy that's creating a huge amount of stars, releasing a lot of energy, but is basically surrounded by an impenetrable layer of dust. And because the scientists behind this paper have only taken a look at roughly around 1/100th of the size of the full moon in the night skies, in other words, imagine the night sky piece that's about this big, and in that tiny piece they discovered at least one hidden galaxy. It suggests to us that in the entirety of the night sky we'll be able to discover a lot more of these hidden giants, thus explaining where all of these mysterious ancient massive galaxies came from. Which of course means that they're there, we just can't really see them. They're all just hidden by this dust all over the universe. And because of the technique used in this paper, I'm sure in some of the future papers we'll be able to discover even more amazing things that we didn't really know possible. This discovery is definitely something that's going to transform the way that we look at the rest of the universe, especially the universe after only about 1 billion years of existence. Hello wonderful person, this is Anton, and in this video we're going to be talking about a galaxy that's relatively close to us, but is never really talked about very often. A galaxy that's not very well known, even though it is quite easily visible. We are also going to talk about a discovery coming from this galaxy that helps us explain how certain stars form. So what you're looking at right here is our representation of the Milky Way galaxy, our own home. Now by now I think pretty much almost everyone is familiar with the Andromeda galaxy, which can be seen right there in the night skies. It is relatively far from us, it's about 2.5 million light years away, but at the same time it's very well known. Now I'm not entirely sure why the Andromeda became so popular over the years, but it is larger and possibly more massive than the Milky Way, and it's also of course on a collision course with our galaxy. But if you look nearby, if you look around, you will discover a galaxy that we're talking about today. It's actually not very far from Andromeda, and specifically it's somewhere right here in this region. And this is the Triangulum galaxy, a galaxy, as you can see, that's also quite visible, but somehow a lot more obscure and way less known than the Andromeda. This is kind of what the simulated version of this galaxy looks like, but if you were to point your telescope at it, you would see something like this. If you do have a telescope at home and you also have a dark enough skies, you can definitely try to check it out. It's a beautiful galaxy. Here's actually a much more detailed version of this image, and it contains some of the most active regions in the nearby space. It produces a lot of stars, roughly around 5 times faster than the Andromeda galaxy, and it's also a place with a lot of really highly energetic areas. And specifically this region right here that's part of the galaxy is one of the most well-studied and well-known nurseries for basically the creation of new stars. It's very highly energetic, it contains a lot of hydrogen and is quite easily visible. The Triangulum galaxy is also very peculiar because right at the center of the galaxy, just as you would expect, it has a lot of really highly energetic activity. And specifically right there in the middle of this galaxy is an extremely powerful X-ray source that is actually even more powerful than the one in the middle of Andromeda galaxy. But what is really unusual about this galaxy is that even though you would think it's some sort of a black hole, it seems that this galaxy does not contain any supermassive black hole at its center. And the unusual X-ray source is caused by something else, something extremely mysterious. Some scientists suggested that the black hole might be there, just a lot smaller, possibly less than 3,000 masses of our sun, but if that is so, it still doesn't explain what causes this particular X-ray source. So there's at least one mystery we still don't really know how to solve. And by the way, this right here, also known as NGC 604, is also simulated in Space Engine, and you can kind of see it right there. It's a very easily visible nebula-like formation. So this right here is where a lot of new stars are formed, and it's an extremely beautiful and exceptionally bright area of this galaxy. Apart from that, there are actually quite a lot of other really interesting and really unusual discoveries related to this galaxy, which we'll probably cover in some of the future videos, but I think the one that I wanted to mention here is in regards to the biggest stellar mass black hole we've discovered. Basically, a typical black hole that orbits around another object is also in this galaxy, and you can easily find this in Space Engine by looking up an object known as M33X-7. So there's a black hole right here, it's about 15 or over 15 masses of the sun, and it's the largest stellar mass black hole we've ever discovered. Basically a typical black hole that orbits around another object and produces a lot of radiation. But none of this still explains to me personally why this galaxy is just not really popular. It's not really talked about that much. I guess it is a little bit smaller than the Milky Way. It's roughly around 60% the size of our galaxy, and it has about 10 times less stars in general, but it's a very exciting place, and which is why this study that's coming out of Japan is kind of exciting to cover, because we finally are talking about the Triangulum galaxy. So what exactly did the Japanese scientists discover? Well, these scientists were studying the creation of really massive stars. Specifically stars that are so massive that they usually live only a few million years and then explode, producing extremely large and very bright supernova. And actually a star that orbits the black hole I just showed you is one such example. We are not entirely sure how they're formed. There are some speculations that maybe they're formed when several stars combine together, or maybe they somehow form through interactions of various clouds in the galaxy. And so these Japanese scientists were able to not just discover but visually show us how these stars are formed, and all of this is done by looking at the Triangulum galaxy where many stars are formed right now. What they did was zoom into one part of the galaxy right here, where they found these really large clouds of gas, and this gas is slowly coming together. And basically imagine that there are several really large dust clouds, something like 200 light years across, possibly containing over 50,000 masses of the sun in total, all of them kind of slowly colliding into another and creating these large formations. And so they looked at these clouds using various frequencies in various telescopes to make sure that they're not just looking at the visual perspective, but also at the radio frequencies that would be produced by, for example, hydrogen or carbon monoxide or other molecules that are in this area. And after this, they used the data from the Hubble telescope to look at the same area to see what's really there. And what they discovered are these really large bright spots indicating that there are supermassive, extremely large and extremely bright stars that were just formed not so long ago, possibly within about 500,000 years from when we're observing them. And they've basically discovered roughly around 10 stars, all in the same region. All of these are very bright O or B stars, pretty much similar to what you see right here, an extremely powerful, extremely large star that is going to live only a few million years and then explode in a supernova, producing more radiation, more clouds, and materials that might one day form a sun-like star. And so this study definitely showed us visually, and kind of proves once and for all, that these large and massive stars that eventually result in stars like our sun are formed by the collision of these clouds, many of which are happening right now and will be happening for many years to come in the Triangulum galaxy. So this is definitely a place for us to study star formation. Now, it's still not entirely clear what even caused these clouds to form and what possibly led to their collision, but we know that this will probably happen again, specifically in a few billion years from now, when this galaxy has a very high chance of colliding with the Milky Way. As a matter of fact, today there's a lot of evidence to suggest that the Triangulum galaxy, also known as M33, will very likely come in front of the Andromeda and collide with the Milky Way first before the Andromeda galaxy joins and forms a very large, extremely massive galaxy, possibly known as Mildromeda. We don't really have a good name for it yet. But the idea of the collision between Triangulum and the Milky Way is still being explored because we're not entirely sure of what the actual speed of both of these galaxies in relation to the Milky Way is yet. We just know that they're headed our way, we're just not sure who's going to come here first. And if the galactic collision with the Triangulum galaxy does happen first, it's very likely it's going to happen in about 2.5 billion years from today. So by the time when, well, our Earth is probably not going to be habitable anymore, and it's very likely that the sun is still going to be just as bright and as powerful as it is today, possibly even hotter. But it's not going to be a red giant yet. And following this collision, it's very likely that the shape of the Milky Way will change quite a lot, and it's also very likely that once the Andromeda joins in, our galaxy will become something similar to many different elliptical galaxies, like for example M87. It might not have a very regular shape, it might be very different from what we even imagine today, but it's probably not going to be a typical spiral galaxy for quite a long time, until gravity stabilizes its shape. Hello wonderful person, this is Anton, and in this video we're going to be talking about the part of the universe that we almost never talk about. The really dark and very mysterious part of the intergalactic space. Today I'm going to talk about what we know about it, but I guess there's going to be a lot of things that we still don't. Many years ago, when I was still teaching, I asked my students a question: where do you think most of the matter in the universe hides in? Where do you think we can find most of the so-called baryonic or visible matter? And almost automatically, pretty much most of them said that it's in black holes, supermassive or ultramassive black holes like the one you see on the screen. This is Sagittarius A star in the middle of our own galaxy. The thing is, that's not even remotely close to the truth. As a matter of fact, we need to really go far away before we discover where most of that mass is. So first of all, only a very small fraction of mass is represented by black holes, because a lot of the mass in the universe is still sort of in gas form. It's basically free-floating. It hasn't really become a star, or was a star and then exploded and this mass was released again. So most of the mass is really just dust and gas like you see on the screen right here, although this is a slightly more exaggerated, more beautiful version of it. Most of it would not even be visible. But also at the same time, if we really wanted to discover the biggest source of mass, we would have to go outside of our own galaxy. We would have to go into the middle of the empty space known as intergalactic medium. So today we're going to be talking about what is really happening here in between galaxies and why this is most likely one of the biggest mysteries we still have, but also hides a lot of answers to everything. Whatever we discover here in the intergalactic medium is actually a lot more important than what we discover in the middle of our own galaxy. So let's begin with the rough representation of the shape of everything in the universe. And what you're looking at here is a randomly selected cube roughly around 100 or several hundred million light years across, and this is the representation of the visible matter in our universe. And every little thread that you see, that's essentially the so-called galactic filaments. Now it might be a little bit difficult to imagine what we're looking at here until we use a simulation known as the Illustris project, which allows us to simulate universe by sort of visualizing various types of radiation spectrum and also of course dark matter. So this is what galaxies would look like. There is a randomly generated elliptical galaxy in the middle there, a few other smaller galaxies around it, and if we were to look at the distribution of gas here, you would see that there's actually a lot of gas present pretty much everywhere around the galaxy as well. But what's more interesting here is if you were to zoom out, with the galaxy still being right there in the middle, but very small now, you would notice that there's actually a lot more gas all over the place in the middle of nowhere. And if we also start looking at dark matter here, we'll realize that they form kind of like these tunnel-like formations that we refer to as the galactic filaments. And these are some of the largest structures out there in the universe. And along these tunnels, or along these filaments, are other galaxies. So pretty much every major galaxy out there in the universe is connected with these filaments filled with gas, occasional stars, a lot of dark matter, and if we were to zoom out here a little bit more, you would start seeing these formations pretty much everywhere. Now, if I were to remove the gas and only leave the stars behind, this is really what it kind of looks like. This is just the dark matter and the visible matter, which is kind of what you're looking at here as well, except that this is in 3 dimensions. And for the most part, if you were to remove all of the galaxies from the picture, you would still be left with roughly around 80% of the entire mass of the universe. And we're talking about baryonic mass only, not even dark matter or anything. So essentially there is more stuff out there that makes up stars and us, of course, that is outside of galaxies than inside those galaxies. So all of this intergalactic space, basically space between galaxies like Milky Way and the Andromeda, is filled with these filaments that you see, and inside of them there's quite a lot of stuff just kind of staying there, and most of this stuff is actively interacting with each other. A lot of it is made up of what's known as ionized hydrogen, mostly because these regions of space are very hot and they create these very highly energized molecules. And a lot of this gas is essentially plasma, the same stuff that you see when you're looking at the sun. Now, it's not as hot as the sun, and it's obviously not as dense as the sun, but it obeys the same principles and still is relatively active as well. And one of the ways we've discovered all of this is because when we were looking at objects known as quasars, these really bright active black hole galaxies that emit a tremendously powerful beam of light, we realized that something was absorbing some of their light, but there was nothing in between those galaxies and us. And as the light from these quasars was passing through these filaments toward our own galaxy, some of the light spectrum was absorbed by hydrogen that it passed through. And we were able to observe this and realize that these filaments are pretty much everywhere. And what's really cool about some of this gas is that it's never actually reacted with anything, in a sense that it never formed any stars or any other objects. In other words, this gas has always been there since the beginning of the universe, and some of it will stay there forever. It will never become a star or any other object, simply because our universe is expanding and this gas is slowly moving farther and farther and farther away from pretty much every major object in the universe. So some of these molecules will always stay just lonely little molecules. But anyway, what else do we know about this? So first of all, as I mentioned, these filaments form pretty much these major structures in the universe, and some of them are some of the biggest structures we've ever seen, hundreds of millions of light years across, spanning almost the entire size of the universe. In between these structures, however, there are these really unusual voids. Now, one of the biggest requests I get on the channel is to talk about the Bootes void, because I've never officially made a video about it. But I have made a video that you can check out somewhere above my head about the so-called local void, which I don't seem to see here, and that's because it's actually a lot smaller and a lot closer to us. But you can see it in this picture with our galaxy being right there in the middle. So these voids are the empty space, or the relatively empty space, in between these filaments. And essentially what you're looking at here can be sort of looked at in this way as well. We have these very large formations known as filaments, galaxies connected to them, and then in between these filaments we get these very large voids, with the closest one being the local void. Boote's void is probably one of the more famous ones, but the local void is a lot more important to us because it's right on our doorsteps. And inside of those voids, once in a while we do find a galaxy or two, but for the most part they're kind of empty and don't really have much gas in them at all. And even in those filaments that I previously mentioned, the density of the gas is not very high. You could, for all intents and purposes, call it vacuum. As a matter of fact, it's even less than vacuum. Let me give you a comparison. If we were to take a cubic centimeter of volume, which is really small, it's just a little bit smaller than a typical sugar cube, and create vacuum inside of this using the best technology we have here on Earth, there would still be roughly around 10 billion atoms on the inside. So even though we call it vacuum, it's not really vacuum. Then let's compare this to the middle of interstellar space, where Voyager 1 and Voyager 2 probes are right now. Here, vacuum can be anywhere between 1 particle per cubic centimeter to roughly around 1 million particles inside of these nebular clouds. So it's a lot less than what we can create here on Earth, but still, once again, not really vacuum. It still has at least a few atoms inside. However, if you were to leave the galaxy and then move to the region known as intergalactic space, this is when things get a little bit more interesting. The vacuum here drops dramatically. Here you would only discover one single atom in a cubic meter of space. And essentially there are roughly around 10,000 times less atoms than in the middle of the galaxy. And that's of course where it becomes really interesting, because even though the density of atoms is much less here in the intergalactic space, because there is so much of that space and because there are so many atoms out there, it still forms about 50 to maybe 80% of total mass of the universe. So if you were to combine all of the intergalactic mass into one, it would be bigger than all of the galaxies together. And for many years now, we've been detecting these unusual interactions between various light coming into our galaxy, including the fast radio bursts, FRBs, that seem to be influenced by various parts of galactic filament as they pass through it. And the more interaction we see, the easier it becomes for us to map it and to start understanding the real structure of the universe. Not just a typical galaxy, the whole universe. Everything in it, including the mysterious dark matter and, of course, the visible matter known as baryonic matter. But none of this matter just kind of stays there. As a matter of fact, most of the intergalactic matter constantly interacts with various galaxies. The best way to describe this interaction is by showing you a galactic collision, although this is more of a very dramatic example, but here, most galaxies, they actually absorb this intergalactic matter into themselves constantly, and they always get this gas as a kind of a replenishment for all of the gas they use up to make up other stars. So as the galaxy, as a typical galaxy, forms stars, and for example our own Milky Way forms roughly around 1.6 masses of the Sun every single year, all of this gas has to come from somewhere, and it usually comes from the intergalactic space through these connections via galactic filaments. So in some sense, all of the galaxies are essentially connected. We're literally connected through these invisible bridges, and one day maybe we'll find a way to use them to travel across galaxies. But like really far from now, because we have no idea what's even in there. But more recently we even started discovering things like magnetic fields in them, and a lot of other really interesting things like stars that we normally find in the middle of galaxies. And some of these stars are very important for us, such as for example Cepheid variables that we often use for mapping galaxies and for determining distances. So there's a lot of really unique and a lot of really interesting things going on in these filaments in between galaxies. And even more, we've discovered many different stars in the intergalactic medium, including stars between our own galaxy and the Andromeda. There are at least 670 stars that have already been confirmed, and I'm sure we'll find more as we keep looking. But even today, we still have more questions about this part of the universe than we have answers. There are still a lot of questions about the mysterious dark matter, a lot of questions about how these filaments were formed to begin with, and many other questions related to the eventual fate and the evolution of the entire universe as it kind of flies apart and becomes bigger and bigger. So we believe that one day maybe the universe does kind of rip apart, and this means that all of these filaments will disappear as well. For now though, we don't really know. But what we can do today is continuously study these galactic filaments and of course the mysterious voids, and at the same time simulate them here on Earth using supercomputers. And this way we'll be able to one day understand what's going on and how all of this will evolve in the next few billion years. Hello wonderful person, this is Anton, and in this video we're going to be talking about new research and a new paper that seems to suggest that basically everything in the universe is connected. Literally, connected through a very unusual but currently somewhat invisible filament. So when it comes to stars and constellations and of course galaxies, we do know that many of them are somewhat connected to each other gravitationally. Like for example, if we were to find one of the typical globular clusters here in the Milky Way galaxy, we would find ourselves in something that looks like this. And this is basically a gravitationally connected structure where all of the stars and all of the neutron stars and black holes and everything in the middle here is connected and moves together and never really separates from one another. These are pretty much everywhere around the universe, and we've seen quite a lot of them in our own galaxy. But on much larger scales, we obviously get other gravitationally connected objects, and I guess the most famous one would be this, the galaxy. But it obviously does not stop there, because we've in the last few decades discovered that even galaxies connect to other galaxies. More specifically, the Milky Way, for example, connects to its satellites and to some extent to the Andromeda as well. So basically the Andromeda galaxy, the Milky Way galaxy, and all of the nearby satellites like the Large Magellanic Cloud, the Small Magellanic Cloud, or even this right here, the diffuse Sagittarius spherical galaxy, all of them are connected to the Milky Way through these somewhat invisible but nevertheless present gravitational links, and in most cases we even have actual signs of those links being formed. And you may have seen one of my previous videos about the Magellanic Bridge and the Magellanic Stream. Both of these are actually separate connections between various galaxies. So this right here is a connection between the Large Magellanic Cloud and the Small Magellanic Cloud, which are these two largest satellites of the Milky Way. This right here is the large, and right there in the corner, right here, is the Small Magellanic Cloud. And they do have a connection, and we've seen it several times now. And also these two galaxies have an actual gas connection to our own galaxy, which unfortunately is not shown here. So in the video that I made a few months ago, I did explain how all of this has been found and how we now know that this connection is actually physical. There are even stars between these galaxies that are formed in this gas. But then as you start looking at the larger scales, you get something known as the local group. The local group of nearby galaxies looks something like this in 3 dimensions, and the Milky Way is right there, this tiny spot in the middle, with these satellites being here, and the Andromeda and the Triangulum galaxies being right here. All of them also have their own satellites. This is also gravitationally connected, and we have actually found links, physical links, that connects them as well. Now, today most scientists believe that all of this is sort of propagated through the mysterious dark matter. And there are quite a lot of various evidence that suggests that this is actually true. But it doesn't end here. If you were to zoom out of here even more, you would discover an even larger gravitational connection, forming first a cluster and then a supercluster. This supercluster that we are in is known as the Virgo supercluster. It's actually this right here, and you'll notice that there's this yellow formation. That's the largest gravitational structure we've discovered to date, and it currently has a name. It's known as Laniakea. The Laniakea supercluster is essentially the extremely large gravitational structure that has been reported by using this image right here, and I've also made a video about this explaining what exactly this shows in the past. But the idea here is that, so this is literally an actual structure. It's a physical connection between galaxies, but it also does not stop there. As we just discovered, especially in the recent paper that came out only a few weeks ago, there seem to be even more mysterious connections out there. Something that scientists currently have no idea how to explain, but they do seem to suggest that the connections are even more profound than we previously thought. And in this particular paper coming out of South Korea, what the scientists discovered is that when they looked at the galaxies nearby and compared them to the galaxies that are actually much farther away, specifically roughly around 20 to 30 million light years away from the Milky Way, which would be equivalent to maybe this distance right here. So the galaxies at this distance all seem to also have a very unusual connection that was detected in a very unusual way. So when the scientists behind this paper looked at essentially properties of galaxies, they noticed that many of those galaxies were actually moving and spinning in a very similar pattern. So when they looked at certain galaxies in one direction, they noticed that those galaxies had exactly the same spin and were, for example, moving away from us. Then they looked at other galaxies in a different direction and saw the opposite effect. Those galaxies were moving away from us and also spinning in a different direction as well. And their spins and their motion was actually correlated, as if something was mysteriously causing them to move and rotate in a very similar fashion, even though they were really far away from one another. So at this distance here, there was some sort of a mysterious force causing these galaxies to behave in a very similar way, and it can't be just explained by galactic gravitational forces. It has to be something else. And one of these suggestions and one of the explanations so far is that it definitely has to relate to something known as the galactic filaments. The video about the filaments should be popping up somewhere right there, but essentially, in a nutshell, what this refers to are these formations that you see right here. This is from the beautiful Illustrious project, which created one of the most realistic, if not the most realistic, simulations of a universe. And this simulation of the universe shows us that there have to be these very unusual formations, these filaments, that are formed by the combination of this blue stuff that you see here. This is the dark matter, mixed with the actual gas that forms stars and obviously other objects as well. And at the same time, all of this is then joined in with the actual galaxies that you see right there. They're barely visible. So all of these galaxies are connected with the gas and dark matter filament. Here's what this image looks like if you were to add all of the gas, and here's what all of this image looks like if you were to add the dark matter. So all of this is not as visible as actual stars because, stars are producing light that we can easily see from really far away, but neither gas nor dark matter produce much. And so we only know, or we only suspect their existence simply by observing the effects. And one of these effects is, of course, this unusual observation that the galaxies seem to have some kind of a strange relationship and connection that causes them to act differently. And in a nutshell, the scientists behind this paper do suggest that there's this unexplained phenomenon that's causing these galaxies to behave in a very similar way. You can find out more about this by reading the paper in the description below. And the thing is, this is not the only thing the scientists have seen in the past few years. We've also observed several other things, like for example, there is an unusual alignment of quasars, or these really bright galaxies, across an even larger distance. We're talking about billions of light years. This is like thousands of more times far away than what we've just looked at. And this was reported by the scientists from Belgium about 5 years ago, and the paper for this you can also find in the description below. But here what they discovered is that even on these larger scales, the actual quasars seem to have a very unusual and somewhat predictable alignment, suggesting that these unusual filaments, or whatever it is, causes the actual galaxies to kind of align, to have a very specific direction and rotation compared to other galaxies at really far away distances. There's almost no way that this happened by chance. It's almost impossible because of the amount of galaxies that they're studied, and also simply because this was a three-dimensional observation in every direction. This wasn't just in one single direction or in a single part of the universe. This was literally by looking this way and then looking that way and seeing a very similar repetitive pattern. Now, all in all, all of this kind of suggests one single thing. The entire universe is connected gravitationally and linked through these unusual formations about which we unfortunately know very little. And one of the reasons we actually do need to study dark matter in a little bit more detail and find out what exactly is happening with it, what it's made out of, and what it does to the universe is because it literally seems to have this effect on the entire universe. It controls the actual galaxies, it controls everything in the universe, and by being able to control dark matter, or at least in some way manipulate it, we might be able to find a way to control the universe. And to quote one of the characters from Frank Herbert the Dune, "He who controls the spice controls the universe," replacing the spice with the dark matter. So it's something that we need to understand if we want to one day become an interstellar and an intergalactic species. Maybe we'll succeed, maybe not. But until we discover something else about this unusual phenomenon and about these unusual effects that we're observing across millions and even billions of light years, that's really it. Check out the papers in the description below, subscribe if you still haven't, share this with someone who loves space and sciences, and come back tomorrow to learn something else. And maybe even consider supporting this channel on Patreon, or by purchasing the beautiful, wonderful person, poster, or t-shirt. I'll see you tomorrow. Come back tomorrow to learn something else. Space out, and as always, bye-bye.